Jnanam Paramam Dhyayam. Knowledge is supreme.
So, now I am going to recall modules of finite length. This is just review. I will not prove the statements, but they will make the statements so clear that you can prove on your own. Okay. So, R is our ring, let me call A as a ring, A is our base ring, always commutative, and M is an A module. You have studied Noetherian modules and also Artinian modules, I suppose, right. So, anyway, let me recall. So, what do you do? For the modules, for a fixed module M, I consider all submodules of that. That is S, I will denote S A M. This is the submodules. N is a submodule, A submodule. And this set, this is a set, and there is inclusion on this set, SAM. With this inclusion, this becomes an ordered set. Ordered set means a set with a relation, and the relation should satisfy three properties, that is reflexive, antisymmetric and transitive. Such a set is called an ordered set. Many books you will find that such are called partial ordered set, but partial word is unnecessary there. So, I dropped it, and more you go to older books, you will not find a word partial. I do not know why it came from. So, ordered set for us is a set with an order on that. Okay, now, in an ordered set, ascending, descending, the chains make sense. So, a module is called Noetherian if every ascending chain becomes stationary, right. And now, when do you call a module to be Artinian? When a descending chain is stationary, right. But now you see, to each ordered set there is a concept of dual. Dual is the opposite order. So, whatever theorem you want to prove for Noetherian, if I change this set to the dual set, that statement will prove. So, the Noetherian will become Artinian and Artinian will become Noetherian. So, you only really have to prove only one theorem. So, if you prove a theorem for Noetherian, then the same theorem will be true for Artinian by just proving, by just changing this set, changing the order to be the opposite order. So, for example, if you want to show that if you have a short exact sequence, so 0, n, m, n prime, if this is short exact, and if the middle module is Noetherian, then the other two modules are Noetherian. So, same statement, if M is Artinian, then these two, if and only these two are Artinian, how will you prove? You just change the order, and this is really neat. Okay. So, now it may happen that you would have seen examples of modules which are Noetherian but not Artinian, and Artinian but not Noetherian. So, if it is both, those modules have nice properties. So, whatever, so module M with the property with ACC as well as DCC. So, Noetherian and Artinian, these models are worth noting. So, what does that mean? That means this means we have when we have such a module, then we have a finite sequence M, which is M0, contains M1, contains, and this cannot go on forever, Mk, and then it becomes 0 and each stage not equal. And also this containment of course not equal, but I want to also assume that there is nobody in between, because if somebody is in between I will insert it. So, that means I will make the chain more and more finer. So, with there exists a chain such that the successive quotients mi by mi plus 1 are simple modules, simple A modules for all I. Simple, you know, simple means there is no submodule other than 0 and the whole module. So, such a series is called a Jordan order series. Such a chain is called a Jordan order series for M. Some people also called it a composition series. Okay, now if you have two such Jordan order series, then this theorem that they have the same length, any two Jordan order series for M are equivalent. Let me write it are equivalent. So, what does equivalent means? So, that is if I have two chains like this, M equal to M0 contained in ML, MK which is 0, and the other one is N equal to N0 NL, this is 0, and here the successive quotients are Mi by Mi plus 1 are simple, here Nj by Nj plus 1 simple, and we call them equivalent if K equal to L and there exist, these guys are permutations of this, that is there exists a permutation sigma on K letters which is L letters. So, S K, these are the permutations on K symbols such that Mi by Mi plus 1, this is isomorphic to N sigma j by sigma j plus 1, sigma I plus 1. So, up to permutation the successive quotients are same, isomorphic. Such a two such series are called equivalent. So, Jordan order theorem says that any two Jordan-Holder series for a module are equivalent. So, in particular they have the same length, and this is called the length of a module. So, I will not prove this theorem. So, prove this, either do it yourself or see some standard book, see maybe R.T.M. MacDonald if you like. So, that is called the length of a module. So, I will write that symbol by length L, just to remember which ring we are working on, and this is the length of M. This is called the length of these are called modules of finite length, because length should make sense, and to make in order that it makes sense, we have to assume the modules are of both, it should satisfy DCC and ACC. So, in particular when your base ring is a field, suppose your base ring is a field, then when will a module M means now K vector space, when will it satisfy ACC and when will it satisfy DCC? When it is both finite dimension. So, length of A by M, in that case this is nothing but the dimension of that module, dimension of the vector space M. So, this makes sense when it is a finite dimensional vector space. So, now going back to our assumption on R naught. See, R was a graded ring, and as an algebra over R naught, it is generated by finitely many elements. This one came because R is Noetherian. That was our assumption original. So, this forces that R naught should be Noetherian, but I want to assume even in more we are in a above exposition, we have assumed R naught is actually a field. But I could have also assumed that R naught is actually finite K algebra. Remember, finite means finitely generated as a module, that means as a vector space it is finite dimensional, and in that case the dimension, see, we have in a Poincare series we have this dimension over K of these modules MMs. So, now these MMs are finitely generated modules over R naught, and if I assume R naught is actually finite dimensional vector space, then this dimension I will have to replace by the length over R naught. This will make sense because this is a finitely generated module and this R naught is a Artinian ring, and therefore it is Artinian, and this length will make sense because it will have, it is Noetherian and also Artinian. Therefore, this length will make sense, and in the above theorem everywhere only a definition will have to replace dimension by this length, and all other induction etc. everything will go through in the calculation. You have a graded module, no? The graded module we started with. See, we had a graded ring and a graded module over that, and we are assuming R is Noetherian, M is Noetherian, and then we defined PM, and in the definition of PM this was the coefficient of Z power M. So, in the general case now you will have to replace this dimension by the length, because if you see the proof of that, it will depend on the Jordan-Holder series. So, every time successive quotient. So that is, just make that change and check whether the same proof will go through if you make a change, replace dimension by this length. Okay. So, yes, R naught is a field, but I am saying now you can even assume now R naught is a finite K algebra. That R naught is a field, but we have used for a definition, no, because I have used the word dimension there. We have, that is what I said, for a definition of a Poincare series, we have, the way I have written, we have used that they are finite dimensional K vector spaces, right. So, R naught was our K, otherwise Poincare series M, what we have to define it as summation summation running over M. Now, length of R naught over of M, mm, and then Z power M. Now, see earlier when R naught was a field, here I had, it was a dimension. Now, I am saying you take this as a new definition, and this definition. So, what we did there was the properties of the dimension, and here also you will have to use the properties of the length. And what properties? When we have a exact sequence, short exact sequence, length of a middle module is length of the sum from the other two modules. And if you have a long sequence, then the length, and if you take alternating signs, then it should be 0. The same proof will be the same. Okay, so I will not go into that details. Okay, so first of all, if you assume R is standard graded, that means R, now I will use R naught. R as a R naught algebra generated by x1 to xn on all xi's, all x1 to xn, they are actually degree 1 element, R1. That is why the standard word. Okay, so sometimes it is also written that this R is as a R naught algebra generated by R1, and R1 is finitely generated R naught module, therefore it is, you can choose finitely many elements. Okay. So, in this case the Poincare series for any graded module M Pm then looks like some Laurent polynomial Q, and all now will be 1 minus Z power n, right, because this will be 1 minus Z power gamma 1 is 1 and so on. So, there are n of them. So, now but there may be, now see this Q is a Laurent polynomial. Maybe this 1 minus Z may be a factor of this and so on and so on. So, I want to reduce right in the middle. So, first of all I want to define a new function. This is Pm, this is P1m, P1m. You will see why I want to do this. This is just Pm, one factor I want to add more, 1 minus Z. This is same as Q by 1 minus Z power n plus 1. And this will be, which is power series Zm. This is a power series, right? Think of it as a power series, and this is also power series. This is the power series 1 plus, remember this formula, 1 minus 1 over 1 minus Z is 1 plus Z plus Z square and so on. So, the coefficients here they are, I will denote them by H1 m at m. And what is H1 m at m? See here, what was it originally? It was only the length or dimension, and here now it will get added up, because when I multiply by this power series, this 1 over this, when I multiply by this power series, they will get added up. So, this H1 m will be equal to dim k mi, and I will be up to m. Okay. Now, I am still writing dimension over k, that is because we are assuming this R naught is actually finite k algebra. If R naught is a finite k algebra, if the dimension, what is the relation between the dimension and the length? Then length over R naught will be length over R naught of a module will be this dimension, length over R naught. So, if you take now first length of R naught over R naught, this is just a dimension of R naught. Alright, so now with this simplification, now what do I do? Now this we have seen this Pm is a rational function of a particular type, and this is further rational function. Now I want to use the partial fractions. I want to use partial fraction. So, partial fraction, you remember what is partial fraction? Partial fraction decomposition of a rational function. See, I will just remind you that we have done this many times. For example, let me give you a simple example. You remember when you wanted to solve integration of rational functions. So, you wanted to solve integration of ft by gt, this, what did you do? You wrote the denominator polynomial, you make split, and then so simple. So, then in a quadratic case you did this, no, x this t minus a, t minus b, and 1 over this. First you divide this polynomial f by g, and then assume that the degree is smaller, degree of the denominator is smaller than the degree of g, and then look at this you wanted to write somebody here t minus b, right, and you made a computation and you see. So, if it was a power here, then you wanted to do this, and also you wanted to add square term and so on, right. So, this was, and why did you do that? Because the integration of these individuals became easier. But very important assumption what we have made is the denominator polynomial in that rational function splits into linear factors, right, which is not true for example real polynomials. But real polynomials, it is not too bad because they are either a linear factor or a quadratic factor. But rational polynomials or polynomials over other fields, and that is why D'Alembert stated the fundamental theorem of algebra. He wanted to prove fundamental theorem of algebra precisely for this reason, not because of any algebraic reason. He wanted to compute integration, and therefore, he was looking for such a partial fraction decomposition so that integration calculation becomes easier. Therefore, he stated that time fundamental theorem of algebra, and he was only using over reals, but if you prove for complex numbers, for reals also it follows. Fundamental theorem for algebra for reals is every polynomial with real coefficients splits into linear and quadratic factors. Okay. So, that was, so this is what we are going to imitate for this rational function Pm. So, what will happen then? So, we have this P1m and we have written it like q by 1 minus z power n plus 1, and remember this n is the number of algebra generators for R, and this is also we have written it as a series h1m at m z power m. Alright, in this I know now the first, so the first is I am going to divide the q by this and then write this as some polynomial p by the remaining one, the remainder divided by this, the denominator. But in that I am also going to use, so this p is what? P is the unique polynomial, Laurent polynomial, which I got after dividing by this, right, and then some more terms will come. Those terms, in those terms I want to use this formula. This is the decomposition of this partial fraction. So, 1 by 1 minus z power in general nu plus 1. What is the formula for this? This is the sum over m, m choose nu z power m. This is more general than 1 minus z, no. So, this formula I am going to plug it in here and then rewrite this term. So, what will I get? And I want to compare, and after that I will compare the coefficients of z power m, because then I will get a power series when I write this formula, and then I have this power series, then I will compare the coefficients. So, what will be the coefficients? Okay, so the coefficients will be, they will look like this, h1m, this one is like this one is also like this, h1m at m, this will look like when I use this formula and then compare. So, some integers and then this coefficient m plus nu, and this sum will run from nu equal to 0 to somebody, because you see it is a power series. This way, what did I do on the left side? I first divided by this z 1 minus z power n plus 1 to this Laurent polynomial and got this Laurent polynomial. So, there is now no 1 minus z power that divides, and then I use or directly if you want, q is a Laurent polynomial and take this 1 minus z power n plus 1 and then use this formula and then compare the coefficient of z power m on both sides. So, here these binomial coefficients will come and they will come with, when I made a division. So, this d is a unique integer, and this E0 to ED, they are integers and ED is non-zero. Coefficients of, yes, they all depend on q and also the whether 1 minus z divides or the, okay. But this also, this formula holds only for large m. You see, because this q has negative terms, no. So, when you compare, I want to compare only for the large power, so that the negative coefficients are not playing any role. And you see this the left side is a length or dimension. So, which is the non-negative integer. So, from this formula it is clear that this h1m, we will see an example for calculation. H1m, this is actually asymptotically equivalent to ED, and this when you expand the binomial, it is m power d by d factorial, asymptotic. Asymptotic means for large. See, because when the m is smaller, then in this binomial expansion, the terms will not contribute to the large one. So, they will be smaller and smaller. No? So, this in particular implies that this ED is positive, because this side is, the sign is determined by the leading term. So, that is, this ED is positive. Now, this d, this integer d which I got out of this, that I will prove it is the dimension. So, that will give us a nice theorem that how do you compute the dimension. Okay, so, that is, so let me write this formally as a corollary. So, that what corollary we have proved is the following. So, R is standard graded, R naught x1 to xn, degree of xi is 1, and m finite graded R module. Then there exists unique integer d, actually natural number d, which is dm, it depends on m. So, natural number and integers is e1 to ed in z with ed positive. This is if d is positive, such that h m at m, which is the dimension over k of mm, this is equal to summation from nu equal to 1 to d e nu m plus nu minus 1 c nu minus 1 for large m. Now, here the only difference I made is here you remember we have computed h1. H1 is sum of the dimensions. From h1, if you want to compute the dimension, you just take the derivative, it is called derivative. So, that means you take h1 m plus 1 minus hm, and you will get, see how are you going to get, remember this h1 m at m, this is the dimensions I less equal to m. So, if I take m plus 1 and subtract h1 m from that, I will get this h1. So, we have this formula h1 m plus 1 minus h1 m, this is h m at m. M or m plus 1, so it is good, m here and m minus 1 here. So, here you see it's the top degree term will get cancelled, that is why No, that is why it is here the nu minus 1. See, you have to also use the binomial coefficients formula. So, it is this. Okay, so, this polynomial, this HM, this is a polynomial. So, also, so the polynomial H M M, this is a polynomial in M. You see, it is visible here because it is here, it is this formula. It is a polynomial in M of degree D. This one is a polynomial, this polynomial is called the Hilbert-Sample polynomial. Of M. Now, let us see one example at least. So, we will get accustomed to the calculation. So, example, let us take K is a field and let us take our ring, graded ring, to be the standard graded ring, which I will denote x, not one variable but many variables, x1 to xn, and let us take module also, that M is also the same. So, M is a graded module and it is standard, R is standard graded K algebra. In this case, R naught is K. Okay, so what is P of Kx? That is what we want to compute, right? What is the definition of P of Kx? So, this is a series. So, this series is what? So, what are the coefficients of z power m? The coefficients here are precisely what? Dimension of over K of mm. This is running over m. So, you need to compute what is the dimension of mm. So, what is mm? Mm is homogeneous components of degree m, and what is that? What is the coefficient? What is this? This is a binomial coefficient, right? This is m plus n minus 1, choose n minus 1. You see, you can test it, take one variable. So, what is one variable case? So, n is 1, then it should be what? M, 1 only, right? So, it is m plus 0, choose 0, which is 1 always. So, it is actually the series 1 plus z squares and so on. So, which is also, so this one is, and what is this then? This one is nothing but 1 by 1 minus z power n. This we have proved it. This is the Poincare, the Laurent polynomial is 1 in this case. So, it is this. So, what is d in this case? D is n, and which is, of course, this n is nothing but the cool dimension of our ring. This we have proved it. In the last lectures we have proved, if you take a polynomial ring over a field, then the cool dimension is n. Okay, and what is En? What is, now it has coefficients up to En. So, En is n is 1 and all other coefficients are 0 for all I less than n in the corollary which we have stated, because it is only this only this, and so the remaining coefficients are 0. So, this is what, and now you could also compute an example where you take a polynomial ring and choose one homogeneous polynomial of some degree and go mod that and calculate. You take f homogeneous polynomial of degree d of degree not, I do not want to call it degree r, and take r to be equal to polynomial ring in n variables modulo f ideal generated by f. This is your graded ring. And now do calculate P r first. And how will you calculate PR? PR, you to calculate PR, you calculate, the for the P of the polynomial ring and this f degree r. So, use that multiplication by f and that kind of argument, and then you will calculate. Then the rest is the numerical calculation with the polynomials.